Right now, as you sit watching this video, you're experiencing what seems like one of the most powerful forces in the universe. Gravity pins you to your chair, holds Earth's atmosphere in place, keeps our planet orbiting the sun, and binds together galaxies containing hundreds of billions of stars. The gravitational pull of black holes warps space-time so severely it stops time itself and tears apart anything that ventures too close. Gravity shapes the cosmic web spanning billions of light years, orchestrates the birth and death of stars, and will ultimately determine the fate of the entire universe. Yet here is the mind-bending truth that will shatter your perception of reality. Gravity is by far the weakest force in the universe, so pathetically feeble that it defies all logic why it has any effect on anything at all. The numbers are so staggering, they seem like a cosmic joke. Gravity is approximately 1,036 times weaker than electromagnetism. That's a 1 followed by 36 zeros. To put this in perspective, if electromagnetic force were represented by the entire observable universe, gravity would be smaller than a single proton. The weak nuclear force, responsible for radioactive decay, is 1,032 times stronger than gravity. Even this weak force makes gravity look like a rounding error in the calculations of reality. But here is what makes this weakness truly disturbing. Despite being comprehensibly feeble compared to other fundamental forces, gravity dominates the large-scale structure of the universe. It holds together stars massive enough to forge heavy elements in their nuclear furnaces. It binds galaxies containing trillions of solar masses. It curves space-time across cosmic distances and will eventually determine whether the universe expands forever or collapses back on itself. How can the weakest force in physics be the dominant architect of cosmic structure? Dr. Steven Weinberg, Nobel Prize winner and architect of the Standard Model, describes gravity's weakness as the most profound mystery in fundamental physics. The mathematical frameworks that successfully describe strong nuclear forces, electromagnetic interactions, and quantum mechanics all break down when trying to explain why gravity is so incredibly weak compared to other forces. This isn't just a curious detail about physics. It is a fundamental puzzle that challenges our understanding of why reality works the way it does. Consider the absurdity of your current situation. You're held in your chair by Earth's gravitational field, the collective pull of an entire planet containing 6 times y kilograms of matter. Yet you can defeat this planetary force field by simply standing up, using nothing more than the electromagnetic forces in your muscle fibers. Your muscles overcome the gravity of an entire world without breaking a sweat. A small refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. These everyday examples reveal just how ridiculously weak gravity actually is. The weakness becomes even more bizarre when you examine atomic structure. The electromagnetic force between an electron and proton in a hydrogen atom is approximately 1,039 times stronger than their gravitational attraction. If gravity had the same strength as electromagnetism, atoms would be crushed out of existence instantly. The delicate balance of forces that allows electrons to orbit nuclei and form the chemistry necessary for life depends entirely on gravity being almost impossibly weak. But the mystery deepens when we consider that gravity's weakness appears precisely tuned to allow complexity and consciousness to exist. If gravity were even slightly stronger relative to other forces, stars would burn out too quickly for life to evolve. If it were weaker, stars wouldn't form at all, leaving the universe a cold, dark collection of dispersed hydrogen and helium. The ratio of gravity's strength to other forces falls within an incredibly narrow range that permits the existence of stable stars, planetary systems, and the billion-year timescales necessary for biological evolution. Recent discoveries in particle physics and cosmology have made gravity's weakness even more puzzling. Dark matter, which comprises 27% of the universe, interacts gravitationally, but appears immune to electromagnetic and nuclear forces. Dark energy, representing 68% of cosmic content, affects space-time expansion but remains mysterious to all known physics except gravity. These findings suggest that gravity might be the only force that interacts with hidden aspects of reality that comprise 95% of the universe. The Large Hadron Collider at CERN has probed the fundamental structure of matter at energies approaching those that existed moments after the Big Bang. Yet gravity remains conspicuously absent from high-energy particle interactions. While electromagnetic, weak nuclear, and strong nuclear forces can be studied and measured in particle colliders, gravity's effects are so feeble, they're completely negligible in laboratory conditions. It's as if gravity operates by entirely different rules from the other fundamental forces. String theory and other attempts to unify physics suggest that gravity's weakness might result from its interaction with hidden dimensions of space that we can't directly perceive. In these theories, gravity leaks into dimensions beyond our familiar three-dimensional space, diluting its strength in our observable reality. If true, this would mean that gravity is actually much stronger in the full-dimensional structure of reality, but appears weak to us because most of its influence spreads into inaccessible spatial dimensions. The implications extend far beyond academic physics. If gravity is indeed the weakest force, why does it dominate cosmic evolution? How does such a feeble interaction manage to overcome the much stronger electromagnetic and nuclear forces that govern matter at small scales? What does gravity's mysterious weakness tell us about the deep structure of reality, the possibility of hidden dimensions, and the fine-tuning that makes consciousness possible? If you are fascinated by the deepest mysteries of physics and want to understand how the universe's weakest force became its most important architect, subscribe and hit thumbs up. And here is a question that will haunt your understanding of reality. If gravity is so incredibly weak, what does this tell us about the hidden structure of the cosmos, that 95% of the universe remains invisible to all forces except gravity? Comment below with your thoughts on whether gravity's weakness reveals hidden dimensions or deeper mysteries about the nature of space and time itself. What we're about to explore goes beyond comparing numbers and forces. We're reinvestigating a fundamental puzzle that touches the deepest questions about reality. Why do the basic forces of nature have such drastically different strengths? How can the weakest force shape the largest structures? And what does gravity's mysterious feebleness reveal about the hidden architecture of existence itself? The journey ahead will take us through the shocking mathematics of force comparison, the quantum realm where gravity virtually disappears, the cosmic scales where weakness becomes dominance, and the profound implications for consciousness in a universe where the forces are arranged in such a peculiar hierarchy. We'll discover why gravity's weakness might be the most important feature of reality, the delicate foundation that makes stars, planets, life, and thought possible. This isn't just a story about physics and numbers. It's an investigation into why the universe seems designed with such precise weakness that complexity can emerge, why consciousness can exist, and why reality operates through such a bizarre arrangement of forces that the weakest one ends up being the most cosmically important. By the end of tonight's exploration, you'll understand why physicists consider gravity's weakness not just surprising, but profoundly mysterious. A clue that our understanding of space, time, and the fundamental structure of reality remains incomplete. More importantly, you'll grasp why this weakness might be the most crucial feature of the universe, the delicate foundation upon which everything you know and love depends. Now, let us begin our journey into the paradox of power and weakness that lies at the heart of cosmic reality. Chapter 1. Deceptive Power. The power that is. First shock about gravity is realizing that what feels like overwhelming power in our daily lives is actually evidence. of just how incredibly weak this force really is. When you feel Earth's gravity pulling you downward with irresistible force, you are not experiencing gravity's strength. You are experiencing the cumulative effect of an entire planet's worth of matter, barely managing to create a noticeable force despite gravity's pathetic weakness. To understand just how deceptive gravity's apparent power is, let's examine what it actually takes to create the gravitational effects we experience every day. The Earth beneath your feet contains approximately 6 kilograms of matter. That is 6 followed by 24 zeros kilograms. This enormous mass includes everything from the iron core 6,000 kilometers below your feet to the rocks and soil at the surface. Every single atom in this massive planetary collection is contributing its tiny gravitational influence to pull you downward. Yet despite this staggering amount of matter working together, the resulting gravitational acceleration is only 9.8 meters per second squared. This might seem substantial, but it reveals gravity's profound weakness when you realize that this is the best an entire planet can do. Dr. Richard Feynman illustrated this weakness by pointing out that you can easily overcome Earth's entire gravitational field by jumping. Your leg muscles, using nothing more than electromagnetic forces between molecules, can defeat the collective gravitational pull of 6 kilograms of planetary matter. The deception becomes even more obvious when you consider magnetic forces. A small neodymium magnet weighing just a few grams can lift a paperclip against the gravitational pull of the entire Earth. The electromagnetic force generated by this tiny magnet overwhelms the gravitational force of a planet containing a trillion atoms. This everyday demonstration reveals that electromagnetic forces are incomparably stronger than gravitational forces. Dr. Brian Greene uses another striking example to illustrate gravity's deceptive weakness. If you rub a balloon on your hair and use it to pick up small pieces of paper, you're witnessing electromagnetic forces easily overcoming gravity. The slight electrical charge on the balloon creates forces strong enough to defeat the gravitational pull of our entire planet. A few extra electrons on a balloon can overcome the combined gravitational effect of every atom in Earth. The mathematical reality behind gravity's weakness becomes clear when we examine Newton's law of universal gravitation. F equals gm1 times square meter, r squared. The gravitational constant g has a value of approximately 6.67 times 1011 cubic meters, kg squared. This tiny number reveals that gravity is inherently weak. Even massive objects separated by small distances create relatively modest gravitational forces. Compare this to Coulomb's law for electromagnetic forces, where the constant K is approximately 9 Yn square meter C. The electromagnetic force constant is about 20 orders of magnitude larger than the gravitational constant. But the real shock comes when you calculate the gravitational force between everyday objects. The gravitational attraction between two 70-kilogram people standing 1 meter apart is approximately 3.3 times 10⁷ newtons. That's 0.000000000000003 skin cells. Two human beings exert less gravitational pull on each other than the static electricity from walking across carpet exerts on a balloon. Recent experiments by Dr. John Price and his team at the University of Colorado have measured gravitational forces between laboratory masses weighing several kilograms. These extraordinarily precise measurements revealed that even with carefully controlled conditions and sensitive instruments, gravitational forces between human-scale objects are almost impossibly difficult to detect. The experiments require isolated underground laboratories, vibration isolation systems, and months of careful measurement to detect gravitational effects that electromagnetic forces would produce instantaneously with easily observable magnitudes. The weakness becomes even more apparent when we consider what's required to create noticeable gravitational effects. The Moon, with a mass of 7.351,022 kilograms, can barely manage to raise ocean tides by a few meters. This effect requires an object weighing 7,500 kilograms positioned 384,000 kilometers away. The gravitational influence of this enormous mass at that distance creates forces so weak they can only move water, the most fluid substance readily available on Earth's surface. Dr. Kip Thorne's calculations of gravitational wave detection illustrate just how incredibly weak gravitational effects are. The deceptive nature of gravity as apparent strength becomes clear when you realize that most cosmic structures that seem to demonstrate gravity as power are actually demonstrations of its weakness. Stars exist because gravity is so feeble that it takes enormous amounts of mass and millions of years to compress hydrogen enough to initiate fusion reactions. If gravity were stronger, stars would collapse instantly into black holes before fusion could begin. If gravity were weaker, stars would never form at all. Galaxies provide another example of gravity's deceptive power. The Milky Way contains approximately 400 billion stars with a total mass of about 1,012 solar masses. Yet this enormous collection of matter creates gravitational fields so weak that individual stars maintain stable orbits for billions of years. Our Sun orbits the galactic center at 220 kilometers per second, but completes only one orbit every 225 million years. This leisurely orbital motion results from gravity being too weak to pull stars rapidly toward galactic centers. The supermassive black hole at the center of our galaxy, Sagittarius A*, contains more than 4 million solar masses compressed into a region smaller than Mercury's orbit. Yet even this extreme concentration of matter creates gravitational effects that are barely detectable from Earth's distance. The Event Horizon Telescope required a planet-sized network of radio telescopes working together to observe the gravitational effects of this massive object on nearby matter. Dr. Andrea Ghez, who won the Nobel Prize for observing stars orbiting near Sagittarius A*, spent decades tracking stellar motions to demonstrate the black hole's gravitational influence. Her measurements required the most advanced telescopes and decades of careful observation to detect gravitational effects from an object containing 4 million times the mass of our Sun. This extraordinary effort was necessary because gravity is so weak that even extreme concentrations of matter produce subtle effects that challenge our best observational capabilities. The cosmic microwave background radiation provides another perspective on gravity's deceptive weakness. This ancient light preserves imprints of gravitational effects from the early universe, when matter was distributed more uniformly than today. The temperature variations in this background radiation are less than 0.000 degrees. Yet they represent the gravitational effects that eventually grew into today's cosmic structures. Gravity was so weak in the early universe that it took billions of years to amplify tiny density fluctuations into the galaxies and galaxy clusters we observe today. Computer simulations of cosmic structure formation reveal that gravity's weakness is essential for the gradual, controlled development of cosmic complexity. Dr. Volker Sprengel's Millennium simulation tracked the evolution of cosmic structure over billions of years, showing how gravity's feeble strength allows matter to clump together slowly enough to form stable structures rather than collapsing immediately into black holes. The apparent contradiction between gravity's weakness and its cosmic dominance has puzzled physicists for decades. How can a force so feeble that it can't even prevent you from jumping manage to control the motion of planets, stars, and galaxies? The answer lies in understanding that gravity's cosmic dominance results from its weakness, not despite it. Because gravity is so weak, it can only become noticeable when enormous amounts of matter work together over vast timescales. This realization transforms our understanding of cosmic evolution. The universe's largest structures exist not because gravity is strong, but because gravity is weak enough to allow controlled, gradual assembly of matter over billions of years. The cosmic web of galaxies, the formation of stars and planets, and the stable orbits that make life possible all depend on gravity being just weak, enough to create structure without immediately destroying it. Understanding gravity's deceptive power reveals that we live in a universe where apparent strength masks fundamental weakness, where cosmic dominance emerges from cosmic feebleness, and where the most important force in shaping reality is paradoxically the weakest force in physics. This paradox points toward deeper mysteries about why the fundamental forces have such drastically different strengths, and what this hierarchy of forces means for the possibility of complexity, consciousness, and cosmic evolution. The deception runs so deep that our intuitive understanding of gravity as a powerful force prevents us from recognizing the profound mystery of its weakness. We mistake the cumulative effect of planetary masses for evidence of gravitational strength, when it is actually evidence of just how pathetically weak gravity must be if it requires entire planets to create forces that your muscles can easily overcome. Chapter 2. Force Hierarchy. To truly comprehend how impossibly weak gravity is, we must examine the complete hierarchy of fundamental forces in the universe and compare their relative strengths using precise measurements. When physicists line up the four fundamental forces, strong nuclear, electromagnetic, weak nuclear, and gravitational, in order of strength, the results reveal a cosmic joke so extreme it challenges our understanding of why reality works at all. The strong nuclear force tops the hierarchy with a relative strength of 1 if we use it as our reference point. This is the force that binds protons and neutrons together inside atomic nuclei, overcoming the electromagnetic repulsion between positively charged protons. Dr. Murray Gell-Mann, who won the Nobel Prize for discovering quarks, showed that the strong force is mediated by gluons and operates only at distances comparable to atomic nuclei, approximately 10 to 15 meters. Next comes the electromagnetic force with a relative strength of approximately 1/137th, or about 0.007 compared to the strong force. This precise number, known as the fine structure constant, was called by Richard Feynman one of the greatest damn mysteries of physics, because no one understands why it has exactly this value. Electromagnetic force governs all chemical reactions, molecular bonds, friction, and the behavior of light. It operates over infinite distances, though its strength decreases with the square of distance. The weak nuclear force ranks third with a relative strength of approximately 10 to 6, or 1/millionth, the strength of the strong force. Despite its name, the weak force is still tremendously more powerful than gravity. This force governs radioactive decay, nuclear fusion in stars, and the interactions of neutrinos. Dr. Sheldon Glashow, Abdus Salam, and Steven Weinberg shared the Nobel Prize for showing that electromagnetic and weak forces are actually different manifestations of a single electroweak force at high energies. Finally, at the bottom of this hierarchy sits gravity with a relative strength of approximately 6 times 10^39. That's 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 oh, 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 compared to the strong force. This number is so small, it's virtually impossible to comprehend. If you wrote out gravity's relative strength as a decimal, you would need to write 38 zeros after the decimal point before reaching the first significant digit. Dr. Edward Witten, one of the leading string theorists, describes this hierarchy as the most profound puzzle in theoretical physics. The range spanning from the strong force to gravity covers 39 orders of magnitude, a gap so enormous that it suggests we're missing some fundamental understanding about how forces work. To put this gap in perspective, the ratio between the strong force and gravity is larger than the ratio between the observable universe and the size of an atom. Let us examine what these relative strengths mean in practical terms by comparing the forces acting on a proton inside an atomic nucleus. The strong force binding this proton to neighboring nucleons exerts a force of approximately 10,000 newtons if we could somehow measure it directly. The electromagnetic force from nearby charged particles might exert forces of roughly 100 newtons. The weak force contributes effects equivalent to about 0.01 newtons during certain nuclear processes. But gravity's contribution to this same proton is approximately 1034 newtons, a number so small it defies comprehension. Even if you somehow gathered every atom in the observable universe and focused their combined gravitational pull on a single proton, the resulting gravitational force would still be weaker than the electromagnetic force between that proton and a single nearby electron. The experimental verification of these force ratios has required some of the most sophisticated instruments ever built. At CERN's Large Hadron Collider, particle interactions demonstrate the strong force every time protons are smashed together at nearly light speed. These collisions can break apart protons and reveal the quarks inside, requiring energies that overcome the strong force binding quarks together. The electromagnetic force is measured routinely in every electronic device and chemical reaction. Measuring the weak force requires more sophisticated techniques because it operates only during specific nuclear processes. Scientists use particle detectors to observe radioactive decay, neutrino interactions, and other weak force phenomena. The weak force's effects can be isolated and measured precisely in controlled laboratory conditions. But measuring gravitational forces between subatomic particles remains impossible with current technology. The gravitational attraction between two protons separated by nuclear distances is so incredibly weak that no conceivable instrument could detect it. Dr. Aharon Kapitolnik's experiments at Stanford University represent the most sensitive gravitational measurements ever attempted, yet they can barely detect gravitational forces between objects weighing several kilograms separated by millimeters. The Cavendish experiment, first performed in 1798 and still considered a masterpiece of precision measurement, barely managed to detect gravitational forces between lead spheres weighing hundreds of kilograms. Modern versions of this experiment, like those conducted by Dr. Jens Gundlach at the University of Washington, use sophisticated isolation and measurement techniques to achieve precisions of a few parts per million. Yet even these extraordinary efforts can only measure gravity's effects between macroscopic objects. Detecting gravitational forces at atomic scales remains completely beyond experimental capability. Recent attempts to unify the forces have revealed why this hierarchy is so puzzling. The electromagnetic and weak forces successfully unify into the electroweak force at high energies, suggesting that force strengths can change under different conditions. Grand unified theories attempt to show that the strong electromagnetic and weak forces merge into a single force at extremely high energies, corresponding to the conditions that existed shortly after the Big Bang. But gravity refuses to fit into these unification schemes. while the other three forces become comparable in strength at energies around 1016 GeV, the grand unified theory scale. Gravity remains pathetically weak, even at the highest conceivable energies. Dr. Michael Green and John Schwarz's superstring theories attempt to include gravity in unified frameworks, but they require additional spatial dimensions and energy scales so extreme they may never be testable experimentally. The hierarchy problem becomes even more mysterious when you consider that the fundamental constants determining force strengths appear to be precisely tuned to allow complexity and life to exist. If the strong force were slightly weaker, atomic nuclei would fall apart and only hydrogen would exist in the universe. If electromagnetic forces were stronger, electrons would spiral into nuclei and atoms couldn't form. If the weak force had different strength, nuclear fusion in stars would proceed too quickly or too slowly to produce the elements necessary for life. But gravity's weakness appears most finely tuned of all. Dr. Martin Rees's calculations show that if gravity were stronger by even a factor of 3,000, stars would burn out in 10,000 years instead of billions of years, too quickly for life to evolve. If gravity were weaker by a similar factor, stars would never form because gravity couldn't overcome gas pressure to compress hydrogen clouds enough to initiate fusion. The anthropic principle suggests that we observe this particular hierarchy of force strengths because we exist in a universe where these values allow complexity and consciousness to develop. But this raises profound questions. Why do the forces have such drastically different strengths? Is there some deeper principle that determines this hierarchy? Or do we live in one of many possible universes with different force ratios, observing these particular values only because they happen to allow observers like us to exist? Recent discoveries in cosmology have made the hierarchy problem even more puzzling. Dark matter, which comprises 27% of the universe, appears to interact gravitationally, but shows no evidence of electromagnetic or nuclear interactions. This suggests that gravity might be the only force that couples to hidden sectors of reality that make up most of the universe, mass, and energy. Dark energy, representing 68% of the universe, affects cosmic expansion, but remains completely mysterious except for its gravitational effects on spacetime geometry. If gravity is so incredibly weak, how does it manage to be the only force that interacts with the dominant components of cosmic reality? Why would the weakest force have exclusive access to 95% of the universe's content? The force hierarchy reveals that we live in a reality governed by an arrangement of fundamental interactions so bizarre and extreme that it challenges every attempt to understand why things work the way they do. The gap between the strongest and weakest forces spans nearly 40 orders of magnitude, a range so vast it suggests that our current understanding of forces and their origins remains profoundly incomplete. Understanding this hierarchy forces us to confront the possibility that gravity's extreme weakness is not an accident or a curious detail, but rather a fundamental clue about the deep structure of reality. The precise weakness that makes gravity seemingly insignificant at atomic scales, while allowing it to dominate cosmic scales, might be the most important feature of our universe, the delicate balance that makes complexity, structure, and consciousness possible. Chapter 3. Quantum Weakness. When we examine gravity at the quantum scale where all other fundamental forces reign supreme, something truly bizarre happens. Gravity effectively disappears. In the realm of atoms, molecules, and subatomic particles, gravitational forces are so incredibly weak they become completely negligible compared to electromagnetic and nuclear forces. This quantum weakness of gravity reveals why our most successful theories of particle physics can completely ignore gravitational effects and still achieve extraordinary precision in predicting atomic behavior. To understand just how negligible gravity becomes at quantum scales, let us examine a hydrogen atom, the simplest possible atomic system consisting of one proton and one electron. The electromagnetic force holding this atom together has a strength of approximately 8.2 times 10^8 newtons at the characteristic distance between electron and proton. This tiny force is what creates the chemical bonds that make matter stable, enables the formation of molecules, and allows all of chemistry to exist. The gravitational force between the same proton and electron is approximately 3.6 times 10^47 newtons. That's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 weaker than the electromagnetic force holding the same atom together. Dr. Steven Weinberg noted that this ratio is so extreme that gravitational forces between subatomic particles are smaller than the uncertainties in measuring electromagnetic forces. But the quantum weakness goes even deeper than these already mind-bending numbers suggest. Quantum mechanics introduces fundamental uncertainty principles that make extremely weak forces like gravity completely unobservable at atomic scales. The Heisenberg uncertainty principle, discovered by Werner Heisenberg in 1927, states that certain pairs of properties, like position and momentum, cannot be measured simultaneously with perfect precision. Dr. David Gross, Nobel Prize winner for discoveries about the strong force, calculated that the quantum uncertainty in measuring gravitational forces between subatomic particles exceeds the strength of those gravitational forces by enormous factors. Even if we had perfect instruments with no measurement errors, quantum mechanics itself prevents us from detecting gravitational effects between individual atoms because the uncertainty in measurement would be larger than the effects we were trying to detect. This creates what physicists call the quantum gravity problem. Gravity is so weak at quantum scales that it can't be studied using the same methods that successfully describe electromagnetic, weak nuclear, and strong nuclear forces. While particle accelerators can probe electromagnetic forces between particles with extraordinary precision, the gravitational forces are so feeble they remain completely invisible to any conceivable quantum measurement. The Large Hadron Collider at CERN accelerates protons to 99.9999% of light speed and smashes them together with energies of 13 TeV, trillion electron volts. These collisions create conditions that existed moments after the Big Bang, allowing physicists to study fundamental forces under the most extreme conditions achievable on Earth. Every collision demonstrates electromagnetic forces as particles interact through photon exchange. Strong forces as quarks and gluons reorganize into new particles, and weak forces as particles decay through various pathways. But gravitational forces remain completely absent from these high-energy collisions. Dr. John Ellis, theoretical physicist at CERN, notes that even if gravitational effects existed in particle collisions, they would be billions of times weaker than the experimental precision needed to detect them. The weakness is so extreme that gravity might as well not exist at all in the quantum realm. This quantum weakness has profound implications for our understanding of matter itself. The Standard Model of Particle Physics, our most successful theory describing fundamental particles and forces, completely omits gravity. This theory can predict the properties of atoms, molecules, and subatomic interactions with precision exceeding 1 part in a billion while treating gravity as if it doesn't exist. Dr. Murray Gell-Mann, who developed the quark theory, demonstrated that the strong force binding quarks into protons and neutrons operates at energy scales where gravitational effects are negligible by factors of 1030 or more. The masses of protons, neutrons, and other particles arise from strong force interactions that completely dominate over any possible gravitational contributions to particle masses. The weak force, despite its name, is still vastly stronger than gravity at quantum scales. When neutrinos, nearly massless particles that interact only through the weak force, pass through matter, they demonstrate weak force interactions that are detectable with sophisticated instruments. Yet these same neutrinos experience gravitational forces so weak that no conceivable detector could observe gravitational effects on individual neutrinos. Recent experiments with ultra-cold atoms have pushed quantum measurements to their absolute limits, achieving temperature just billions of degrees above absolute zero and using laser interferometry to detect motions smaller than atomic nuclei. Dr. Mark Kasovich's experiments at Stanford can measure accelerations as small as 10 to 12 meters per second squared. Yet even these extraordinarily sensitive quantum experiments cannot detect gravitational forces between individual atoms. The quantum weakness of gravity creates what string theorists call the hierarchy problem. Why is gravity so incredibly weak compared to other forces? String theory attempts to solve this problem by proposing that gravity operates in additional spatial dimensions beyond our familiar 3 dimensions of space. In these theories, gravity appears weak to us because most of its strength leaks into hidden dimensions we can't access. Dr. Lisa Randall's work on extra dimensions suggests that if space has additional dimensions, gravity would spread out into these dimensions, while electromagnetic and nuclear forces remain confined to our 3-dimensional space. This would naturally explain gravity's weakness without requiring any fine-tuning of fundamental constants. However, experimental tests of extra dimensions require detecting gravitational effects at extremely small distances, measurements that remain beyond current technological capability. The quantum weakness also raises profound questions about the relationship between quantum mechanics and general relativity. Einstein's general relativity describes gravity as the curvature of spacetime itself, treating space and time as a smooth, continuous fabric. But quantum mechanics suggests that at extremely small scales, space and time might be discrete and discontinuous, composed of tiny quantum units rather than smooth geometry. Dr. John Wheeler proposed that at the Fies Planck scale, distances of approximately 10 to 35 meters, spacetime might become foamy with quantum fluctuations so violent they prevent any meaningful description of smooth geometry. At these scales, gravity might become strong enough to participate in quantum effects. But these distances are 20 orders of magnitude smaller than atomic nuclei and completely inaccessible to direct experimental investigation. Loop quantum gravity, developed by Dr. Carlo Rovelli and others, attempts to quantize space and time themselves, treating them as composed of discrete loops and nodes rather than continuous geometry. In this framework, gravity as quantum weakness results from the fact that smooth spacetime geometry only emerges as an average effect when enormous numbers of quantum geometric elements combine together. The implications of gravity as quantum weakness extend beyond particle physics to cosmology and our understanding of the universe as origin. During cosmic inflation, the rapid expansion believed to have occurred in the first fraction of a second after the Big Bang, quantum fluctuations in gravitational fields might have been amplified to cosmic scales, creating the density variations that eventually became galaxies and galaxy clusters. Dr. Alan Guth's inflationary cosmology suggests that quantum uncertainty in gravitational fields during the earliest moments of cosmic history became the seeds for all cosmic structure. But these effects required extreme conditions when the universe was so young and dense that quantum effects and gravitational effects operated at comparable energy scales, conditions that existed only during the first 10 to 32 seconds of cosmic history. The cosmic microwave background radiation preserves evidence of these quantum gravitational effects amplified to cosmic scales. The tiny temperature variations measured by the Planck satellite mission might represent quantum fluctuations in gravitational fields that occurred when the universe was smaller than an atomic nucleus, but were stretched by cosmic expansion to become fluctuations spanning billions of light years. Understanding gravity as quantum weakness reveals that we live in a universe where the most familiar force in our daily experience becomes completely invisible at the scales where matter is constructed. The atoms that make up your body, the molecules that enable your thoughts, and the chemical reactions that power your metabolism all occur in a realm where gravity might as well not exist at all. This quantum weakness might be essential for the existence of stable matter. If gravity were strong enough to significantly affect atomic structure, the delicate balance of forces that allows electrons to maintain stable orbits around nuclei might be disrupted. Chemistry as we know it might be impossible if gravitational effects competed with electromagnetic forces in determining molecular structure. The complete absence of gravity from quantum mechanics, while its dominance at cosmic scales, reveals a universe where different forces operate in completely separate realms. This separation might be necessary for the emergence of complexity, allowing quantum mechanical processes to create stable matter while gravitational processes create cosmic structure without interference between these fundamentally different scales of organization. Chapter 4. Scale Paradox, the most mind-bending aspect of gravity. S weakness is how this incredibly feeble force manages to completely dominate the cosmos, despite being negligible at every smaller scale. This scale paradox reveals one of the most profound mysteries in physics. How can a force so weak it is invisible in atoms somehow control the motion of planets, stars, and galaxies? The answer lies in understanding how gravity's unique properties allow it to accumulate effects across cosmic scales in ways that other forces cannot. The key to gravity's cosmic dominance lies in its universal nature and infinite range. While electromagnetic forces can be positive or negative, allowing opposite charges to cancel each other out, gravitational forces are always attractive and always additive. Every particle of matter in the universe contributes its tiny gravitational pull in the same direction, creating cumulative effects that grow stronger with the total amount of matter involved. Dr. Einstein's general relativity revealed that gravity isn't really a force at all, but rather the curvature of spacetime itself caused by mass and energy. This geometrical interpretation helps explain why gravity can dominate at large scales despite its weakness. While electromagnetic forces involve discrete interactions between charged particles, gravitational effects emerge from the overall geometry of spacetime, which can accumulate small curvatures into large-scale warping. To understand the scale paradox, consider how forces behave differently as we examine larger and larger systems. In an individual hydrogen atom, electromagnetic forces dominate by factors of YY, making gravity completely negligible. But as we build up larger systems, molecules, cells, organisms, planets, electromagnetic forces increasingly cancel each other out, while gravitational forces continue to accumulate. This happens because most matter is electrically neutral overall. When you combine equal numbers of protons and electrons to build larger structures, the positive and negative charges balance out, reducing the net electromagnetic force to zero over large scales. But every proton and electron contributes the same small gravitational effect, and these effects add up without cancellation as you combine more and more matter. Dr. Steven Weinberg calculated that by the time you reach planetary masses, approximately Y8 kilograms, the cumulative gravitational effects finally become comparable to electromagnetic forces. This explains why gravity doesn't become noticeable in everyday experience until you reach the scale of planets. Below planetary masses, electromagnetic forces from the slight excess of charged particles in ordinary matter can overcome gravitational attraction. The scale transition becomes dramatic when you consider stellar masses. Our Sun contains about 2 kilograms of matter, roughly 300,000 times more massive than Earth. At this scale, gravity's cumulative effects become so dominant that they overcome nuclear fusion pressure and maintain the Sun's structure against the enormous internal pressures created by converting 4 million tons of matter into energy every second. But even stellar-scale gravity pales compared to galactic-scale effects. The Milky Way galaxy contains approximately 1,012 solar masses worth of visible matter, plus additional dark matter that interacts only gravitationally. This enormous collection of mass creates gravitational fields strong enough to hold together a disk of matter, 100,000 light-years in diameter, and maintain stable orbital motions for billions of years. Recent observations of galaxy clusters reveal gravity operating on even more impressive scales. The Coma cluster contains thousands of galaxies with a total mass exceeding 1015 solar masses. Dr. Vera Rubin's observations of galactic rotation curves showed that visible matter accounts for only about 15% of the gravitational effects observed in galaxy clusters, leading to the discovery that 85% of gravitational effects come from dark matter that doesn't interact electromagnetically. This discovery reveals another aspect of the scale paradox. Gravity is the only fundamental force that interacts with dark matter. While electromagnetic, weak nuclear, and strong nuclear forces affect only the 15% of matter that we can observe directly, gravity interacts with 100% of cosmic matter and energy. At cosmic scales, gravity becomes the dominant force precisely because it's the only force that couples to most of the universe's content. The cosmic microwave background radiation provides evidence of gravity's large-scale dominance stretching back to the early universe. The tiny temperature variations in this ancient light, fluctuations of only 0.001 degrees, represent gravitational effects that grew over billions of years to become today's cosmic structure. These primordial gravitational fluctuations were initially smaller than quantum uncertainty, yet they dominated cosmic evolution because no other force could operate on such vast scales. Dr. Alan Guth's inflationary cosmology explains how quantum-scale gravitational fluctuations could be amplified to cosmic scales during the universe's first moments. During cosmic inflation, regions of space smaller than atomic nuclei expanded faster than the speed of light, stretching tiny gravitational variations across distances that eventually became larger than galaxy clusters. This process demonstrates how gravity's effects can bridge the gap between quantum and cosmic scales in ways impossible for other forces. Computer simulations of cosmic structure formation reveal how gravity's weakness paradoxically enables cosmic complexity. Dr. Volker Sprengel's Millennium simulation tracked the evolution of cosmic structure over 13 billion years, showing how gravity's gentle influence allows matter to clump together slowly enough to form stable structures. If gravity was stronger, matter would collapse immediately into black holes before complex structures like galaxies and stars could form. The scale paradox also explains why gravity determines the ultimate fate of the universe. While electromagnetic and nuclear forces govern local processes like stellar fusion and planetary geology, only gravity operates on scales large enough to affect cosmic expansion. The current acceleration of cosmic expansion, driven by dark energy, represents a gravitational effect operating on scales encompassing the entire observable universe. Recent observations by the Planck satellite mission reveal that gravity's large-scale effects determine the geometry of space itself. The universe appears to be geometrically flat to within 0.4% precision, meaning that gravitational effects from all matter and energy in the universe precisely balance the expansion rate. This cosmic balance occurs only because gravity is the sole force operating on universal scales. The hierarchy of cosmic structures demonstrates how gravity's dominance emerges gradually as scale increases. At atomic scales 1010 meters, electromagnetic forces dominate by 40 orders of magnitude. At planetary scales YY meters, gravity and electromagnetism become comparable. At stellar scales YA meters, gravity begins to dominate. At galactic scales YA meters, gravity dominates by enormous factors. And at cosmic scales YD meters, gravity is essentially the only force affecting large-scale dynamics. Dr. Sean Carroll's work on cosmic evolution reveals that this scale-dependent force hierarchy is essential for cosmic complexity. The separation of scales allows quantum mechanical and electromagnetic processes to create stable atoms and molecules, while gravitational processes create cosmic structure with minimal interference between these different organizational levels. The scale paradox becomes even more mysterious when you consider dark energy, which comprises 68% of the universe's total energy content. Dark energy affects cosmic expansion through gravitational interactions, yet its effects are detectable only on the largest possible scales. At scales smaller than galaxy clusters, dark energy's influence is negligible, but at cosmic scales, it dominates over all other forms of matter and energy. This suggests that gravity might interact with aspects of reality that remain completely hidden from other forces, while electromagnetic and nuclear forces interact only with the 5% of cosmic content that forms stars, planets, and life. Gravity interacts with dark matter 27% and dark energy 68% that comprise the vast majority of cosmic reality. The scale paradox might exist because gravity is the only force with access to most of the universe as content. Understanding the scale paradox reveals that gravity's cosmic dominance results from its weakness rather than despite it. Because gravity is too weak to significantly affect atomic and molecular processes, it doesn't interfere with the electromagnetic and nuclear forces that create stable matter. But because gravity affects all forms of matter and energy equally and operates over infinite distances, it can accumulate effects on scales where other forces cancel out or become irrelevant. This delicate balance suggests that gravity's precise weakness might be fine-tuned to allow both microscopic complexity and cosmic structure to exist simultaneously. If gravity were stronger, it would disrupt atomic processes and prevent chemistry from working. If gravity were weaker, cosmic structures like stars and galaxies couldn't form. The observed strength represents a narrow range that permits complexity at multiple scales without conflict between different organizational levels. The scale paradox forces us to recognize that we live in a universe where apparent cosmic dominance emerges from fundamental weakness, where the most important large-scale force is negligible at small scales, and where cosmic complexity depends on precise relationships between forces operating at completely different scales. This paradox might be the key to understanding why consciousness can exist in a universe where matter organizes itself into stars, planets, and thinking beings. Chapter 5. Missing Dimensions. One of the most startling proposed solutions to gravity's mysterious weakness suggests that our familiar three-dimensional space might not be the complete story. According to some of the most sophisticated theories in modern physics, gravity appears weak to us because most of its strength is leaking into hidden spatial dimensions beyond our perception. This dimensional explanation for gravity's weakness opens up mind-bending possibilities about the true structure of reality and our place within a larger cosmic framework. The dimensional approach to understanding gravity's weakness emerged from string theory, which requires additional spatial dimensions beyond our familiar three to be mathematically consistent. Dr. Edward Witten and other string theorists realized that if space has more than 3 dimensions, Forces could behave very differently depending on whether they reconfine to our three-dimensional space or can propagate into the extra dimensions. In these theories, electromagnetic, weak nuclear, and strong nuclear forces are confined to our three-dimensional brain, a higher dimensional surface embedded in a space with more dimensions. But gravity, uniquely among the fundamental forces, can propagate freely through all dimensions of space. This means that while other forces remain concentrated in our three-dimensional reality, gravity spreads out into additional dimensions, diluting its strength in our observable space. Dr. Lisa Randall's groundbreaking work on extra dimensions showed that even a single additional spatial dimension could explain gravity's weakness if that dimension has the right size and properties. In the Randall-Sundrum models, space has one extra dimension that's zorked, in a way that traps most matter and energy on our three-dimensional brain, while allowing gravity to leak into the extra dimension. The mathematics become startling when you calculate how much gravity's strength would be diluted by extra dimensions. In a space with one additional dimension, gravitational force would spread out over four-dimensional volumes instead of three-dimensional volumes, weakening it by factors that depend on the size of the extra dimension. If the extra dimension is large enough, this dilution could account for gravity's observed weakness compared to other forces. But the most mind-bending possibility is that gravity might actually be a strong force in the full-dimensional structure of reality, appearing weak to us only because we observe just a tiny fraction of its true strength. Dr. Arkaniham Dimopoulos and Vali proposed that extra dimensions could be much larger than previously thought, possibly even millimeter-sized, while remaining hidden from electromagnetic forces that can access them. In these large extra-dimension models, gravity would be a strong force comparable to other fundamental forces when measured in the complete dimensional space. But since we re-trapped on a three-dimensional brain and can only observe the portion of gravity that operates within our dimensional slice, we perceive gravity as incredibly weak. It is like observing the shadow of a three-dimensional object on a two-dimensional surface. You only see a fraction of the object's true structure. Recent experiments have begun testing these dimensional theories by searching for deviations from Newton's law of gravitation at very small distances. If extra dimensions exist and gravity can leak into them, then gravitational forces between nearby objects should become stronger than Newton's law predicts at distances comparable to the size of extra dimensions. Dr. Eric Adelberger's experiments at the University of Washington have tested Newton's law down to distances of 44 micrometers using sophisticated torsion balance techniques. These experiments look for gravitational forces that are stronger than expected at short distances, which would indicate that gravity is returning from extra dimensions and becoming stronger as you probe smaller scales where extra-dimensional effects become important. So far, these tests have found no evidence for extra dimensions, but they've only probed down to distances much larger than the scales, where extra-dimensional effects are expected to become significant according to most theories. The experiments continue pushing towards smaller distance scales, searching for the regime where gravity's true dimensional structure might become observable. The Large Hadron Collider at CERN provides another testing ground for extra-dimensional theories through high-energy particle collisions. If extra dimensions exist, particle collisions at sufficient energy might create gravitons, hypothetical particles that carry gravitational force that escape into extra dimensions. These events would appear as missing energy in collision debris, providing indirect evidence for gravity's access to hidden dimensions. Dr. John Ellis and colleagues have searched LHC collision data for these missing energy signatures that would indicate graviton production and escape into extra dimensions. While no conclusive evidence has emerged, the experiments have placed limits on the possible size and properties of extra dimensions, constraining theories about how gravity might leak into hidden spatial realms Kaluza-Klein theory, developed in the 1920s, provides the historical foundation for modern extra-dimensional approaches to gravity. Theodor Kaluza and Oscar Klein showed that adding a fifth dimension to Einstein's equations naturally incorporates electromagnetic forces as geometric effects in the higher dimensional space. This early work suggested that all fundamental forces might be different aspects of geometry in a higher dimensional space. Modern versions of Kaluza-Klein theory propose that each fundamental force corresponds to different geometrical effects in spaces with different numbers of dimensions. In these frameworks, the apparent hierarchy of force strengths results from the different ways that forces propagate through the complete dimensional structure of reality. String theory takes this dimensional approach to its logical extreme, requiring 6 or 7 additional spatial dimensions beyond our familiar 3 for mathematical consistency. In string theory, fundamental particles are actually tiny vibrating loops in this higher dimensional space, and their properties depend on how they vibrate in the extra dimensions. Gravity emerges as vibrations that can propagate through all dimensions, while other forces correspond to vibrations confined to lower dimensional subspaces. Dr. Michael Green and John Schwartz's superstring theory suggests that gravity's weakness results from its interaction with the entire 10 or 11-dimensional structure of spacetime, while other forces are restricted to lower dimensional subspaces. This dimensional confinement naturally explains why electromagnetic, weak, and strong forces appear much stronger than gravity from our 3-dimensional perspective. But extra-dimensional theories raise profound questions about the nature of reality itself. If space truly has additional dimensions that we can't perceive directly, then most of reality exists beyond our sensory and instrumental capabilities. We might be like 2-dimensional beings living on the surface of a 3-dimensional world, completely unaware of the vast spatial structure that surrounds our dimensional prison. Recent developments in holographic principle physics suggest an even stranger possibility that higher dimensional spaces might be projections of information stored on lower dimensional boundaries. In these theories, extra dimensions are real spatial dimensions, but rather mathematical descriptions of information processing occurring on the boundaries of space. ADS-CFT correspondence, discovered by Dr. Juan Maldacena, shows that gravitational theories in spaces with extra dimensions can be exactly equivalent to non-gravitational theories operating on the boundaries of those spaces. This suggests that gravity's weakness might result from its holographic nature, appearing weak because it is actually a projection of information processing occurring on distant boundary surfaces. The implications of missing dimensions extend beyond explaining gravity's weakness to questions about cosmic evolution and the nature of consciousness itself. If reality has additional spatial dimensions, then cosmic evolution, biological development, and even the emergence of consciousness might involve processes that extend beyond our 3-dimensional perspective. Some theories suggest that consciousness might involve information processing that extends into extra dimensions, explaining why subjective experience seems to transcend purely physical brain processes. If gravity can access hidden dimensions, perhaps consciousness, which appears to involve non-local correlations and information integration, also operates partially in extra-dimensional space. Understanding missing dimensions forces us to confront the possibility that our 3-dimensional experience of reality represents only a tiny fraction of the total cosmic structure. Gravity's weakness might be our first clue that reality is far vaster, more complex, and more mysterious than our dimensional limitations allow us to perceive directly. The search for extra dimensions continues through increasingly sophisticated experiments and theoretical developments. Whether or not extra dimensions exist, the possibility that gravity's weakness results from missing spatial dimensions reveals how much we still don't understand about the fundamental structure of space, time, and the forces that shape reality. If gravity is indeed leaking strength into hidden dimensions, then every gravitational effect we observe, from falling objects to orbital mechanics to cosmic structure formation, represents just the tip of an iceberg whose full structure extends into realms beyond our perception. This dimensional mystery transforms gravity from the weakest force into potentially the strongest force, hiding most of its power in regions of space that remain forever beyond our direct observation. Chapter 6. Cosmic Architecture. Despite being incomprehensibly weak compared to other fundamental forces, gravity has constructed every large-scale structure in the observable universe. From the formation of the first stars 13 billion years ago to the vast cosmic web spanning billions of light years, gravity's feeble strength has proven perfectly suited for building cosmic architecture that balances stability with complexity. Understanding how the universe's weakest force became its master architect reveals profound insights about cosmic design and the relationship between force strength and structural complexity. The cosmic construction project began during the universe's Dark Age, the period between 380,000 and 150 million years after the Big Bang, when the cosmos had cooled enough for neutral atoms to form, but before the first stars ignited. During this era, gravity was the only force operating on large scales, slowly amplifying tiny density fluctuations left over from cosmic inflation into the gravitational wells that would eventually become stars and galaxies. Dr. Abraham Loeb's studies of early cosmic evolution revealed that gravity's weakness was essential during this formative period. If gravity had been stronger, the tiny primordial density fluctuations would have collapsed immediately into black holes before nuclear fusion could begin. If gravity had been weaker, density fluctuations would never have grown large enough to overcome gas pressure and form the first cosmic structures. The observed strength represents a narrow range that allows controlled gravitational collapse over hundreds of millions of years. The formation of the first stars demonstrates gravity's architectural precision. These population 3 stars formed when primordial hydrogen and helium clouds accumulated under gravitational attraction until their cores reached temperatures of 10 million Kelvin, hot enough to initiate nuclear fusion. Dr. Volker Brahm's computer simulations show that this process required gravity to compress gas by factors of more than 1 trillion while maintaining precise balance against radiation pressure and thermal expansion. Gravity's weakness enabled this delicate construction process by ensuring that stellar formation occurred gradually over millions of years rather than instantaneously. The slow timescales allowed convection, radiation, and magnetic fields to transport heat and organize stellar structure before gravitational collapse could create black holes. Stronger gravity would have made stellar formation too rapid for these stabilizing processes to operate effectively. The stellar architecture created by gravity's weakness has profound implications for cosmic chemistry. Main sequence stars like our Sun burn hydrogen steadily for billions of years because gravity's gentle compression creates internal pressures that precisely balance fusion energy generation. This balance, known as hydrostatic equilibrium, depends critically on gravity being just weak enough to allow controlled fusion rather than explosive burning. More massive stars demonstrate how gravity's architectural capabilities scale with available mass. Stars with masses 8 to 25 times larger than our Sun use gravity's accumulated effects to forge heavy elements through successive fusion reactions: carbon, oxygen, silicon, iron, in nested shells surrounding increasingly hot stellar cores. Dr. Subramanian Chandrasekhar's calculations showed that these massive stars can maintain structural stability through gravity's precise balance of compression and fusion pressure until their cores reach iron, at which point further fusion becomes energetically impossible. When these massive stars exhaust their nuclear fuel, gravity finally overwhelms all other forces in spectacular architectural collapses, Core collapse supernova occur when gravity compresses stellar cores beyond nuclear density in less than 1 second, creating neutron stars or black holes while explosively ejecting outer stellar layers enriched with heavy elements. These explosions distribute the products of stellar nucleosynthesis throughout interstellar space, providing the raw materials for planetary systems and biological evolution. Dr. Hans Bethe, who won the Nobel Prize for discovering the nuclear reactions that power stars, calculated that supernova explosions release approximately 1044 joules of energy, equivalent to the gravitational binding energy of neutron stars. This demonstrates gravity as incredible architectural accomplishment, accumulating enough matter to create gravitational fields strong enough to compress matter beyond nuclear density while maintaining stellar structure for millions of years beforehand. Galactic architecture represents gravity's most impressive large-scale construction project. The Milky Way galaxy contains approximately 400 billion stars organized into a disk structure 100,000 light-years in diameter, maintained by gravitational forces acting on roughly 1,012 solar masses of matter. Dr. Vera Rubin's observations of galactic rotation curves revealed that this architectural achievement requires 5 times more gravitational mass than can be accounted for by visible matter alone. The discovery of dark matter reveals another aspect of gravity as cosmic architecture, the ability to organize matter that doesn't interact electromagnetically or through nuclear forces. Dark matter halos provide the gravitational scaffolding around which normal matter accumulates to form galaxies. Computer simulations by Dr. Carlos Frank and others shows that without dark matter's gravitational architecture, galaxies like the Milky Way couldn't exist because normal matter alone doesn't provide sufficient gravitational attraction. Galaxy clusters demonstrate gravity's architectural capabilities at even larger scales. The Coma cluster contains thousands of galaxies bound together by gravitational forces acting on total masses exceeding 1,015 solar masses. This structure spans 20 million light-years and has remained gravitationally bound for billions of years despite the individual orbital velocities of galaxy members reaching thousands of kilometers per second. Recent X-ray observations by the Chandra Observatory reveal that gravity as galactic cluster architecture includes vast reservoirs of hot gas with temperatures reaching 100 million Kelvin. This intracluster medium contains more mass than all the galaxies and clusters combined, demonstrating that gravity can organize matter across the entire electromagnetic spectrum from cool stellar material to extremely hot ionized plasmas. The cosmic web represents gravity as ultimate architectural achievement, a network of filamentary structures spanning the entire observable universe. Dr. J. Richard Bond's computer simulations of cosmic structure formation show how gravity transforms the relatively uniform matter distribution of the early universe into a complex network of interconnected filaments, nodes, and voids that organizes matter across distances exceeding 1 billion light-years. This cosmic web architecture emerges from gravity's unique combination of weakness and universality. Because gravity is so weak, cosmic structure formation occurs gradually over billions of years, allowing complex hierarchical organization to develop. Because gravity affects all matter equally, it can organize both normal and dark matter into the largest possible structures without preferentially affecting different types of matter. The Sloan Digital Sky Survey has mapped the cosmic web architecture across distances encompassing billions of galaxies, revealing fractal-like structures that repeat at multiple scales. This architectural complexity emerges entirely from gravitational interactions operating according to simple inverse square law physics, demonstrating how weak forces can generate sophisticated organizational patterns when operating over cosmic scales and timescales. Dark energy adds another dimension to gravity's cosmic architecture by affecting the expansion rate of space itself. The accelerating cosmic expansion, driven by dark energy, represents a form of gravitational effect operating on the largest possible scales, the geometry of spacetime throughout the entire universe. Dr. Adam Rees's observations of distant supernova revealed that this cosmic architectural project is currently accelerating, with dark energy's gravitational effects overwhelming matter's gravitational attraction on universal scales. The precision of gravity's cosmic architecture becomes apparent when you consider alternative scenarios with different gravitational strengths. Dr. Martin Rees's calculations show that increasing gravity's strength by just a factor of 3.0 would make stars burn out in thousands of years instead of billions of years, eliminating the stable stellar architecture necessary for planetary formation and biological evolution. Decreasing gravity's strength by similar factors would prevent star formation entirely, leaving the universe filled with cold, dispersed gas. The fine-tuning extends to the relationship between gravity and other forces. If electromagnetic forces were stronger relative to gravity, electrons would be more tightly bound to nuclei, making chemical reactions so slow that complex chemistry couldn't occur within stellar lifetimes. If nuclear forces were stronger relative to gravity, stellar cores would reach fusion temperatures at smaller masses, making long-lived stable stars impossible. Recent studies of exoplanetary systems reveal that gravity's cosmic architecture extends to planetary formation and orbital stability. The Kepler Space Telescope has discovered thousands of planetary systems with architectures ranging from hot Jupiters orbiting extremely close to their stars to multi-planet systems with complex orbital resonances maintained by gravitational interactions over billions of years. Understanding gravity's cosmic architecture reveals that the universe's large-scale organization results from the delicate balance between gravitational attraction and various forms of resistance, gas pressure, rotation, electromagnetic forces, and cosmic expansion. This balance allows gravity to construct stable hierarchical structures from the smallest dwarf galaxies to the largest superclusters while maintaining enough dynamic complexity for ongoing cosmic evolution. Gravity's architectural success demonstrates that cosmic construction requires weakness rather than strength. Strong forces create rigid, static structures or explosive instabilities, while gravity's gentle influence allows the gradual assembly of complex, dynamic, evolving systems that can maintain themselves for cosmic timescales while continuing to develop increasing organizational sophistication. The cosmic architecture built by gravity's weakness provides the stable foundation for all higher order complexity in the universe, from the chemical evolution that creates heavy elements to the planetary environments that allow biological evolution to proceed. Every aspect of cosmic organization that makes life possible depends on gravity being precisely weak enough to allow controlled, gradual construction of cosmic structures without disrupting the delicate force balances that enable complexity to emerge. Chapter 7. Life's Foundation. The emergence and evolution of life throughout the cosmos depends absolutely on gravity being precisely weak enough to allow biological complexity while remaining strong enough to create stable planetary environments. This perfect balance between gravitational weakness and biological necessity reveals that life itself might be impossible in universes where gravity has any significantly different strength. Understanding how gravity as weakness enables biological existence opens profound questions about cosmic fine-tuning and the relationship between fundamental physics and consciousness. Life requires stable planetary environments that can maintain liquid water, atmospheric retention, and protection from cosmic radiation for billions of years, conditions that depend critically on gravity being weak enough to allow complex chemistry, while strong enough to hold planetary systems together. Dr. James Casting's studies of planetary habitability reveal that this gravitational balance spans an incredibly narrow range, compared to the vast hierarchy of force strengths in nature. The chemical foundation of life emerges from electromagnetic forces between atoms and molecules, processes that require gravity to be weak enough not to interfere with chemical bond formation. If gravity were strong enough to significantly affect atomic structure, the electromagnetic forces that govern chemistry would be overwhelmed by gravitational effects. Chemical bonds depend on precise energy differences between electron orbital configurations, differences that would be disrupted by gravitational fields strong enough to compete with electromagnetic forces. Dr. Harold Morowitz's calculations of the energy scales involved in biochemistry show that molecular processes operate at energy levels where gravitational effects between individual molecules are negligible by factors of 1037 or more. This enormous separation of energy scales allows complex chemistry to proceed without interference from gravitational forces, enabling the intricate molecular machinery that powers living systems. But life also requires gravitational effects at larger scales to create and maintain planetary environments. Earth's gravity is strong enough to retain water vapor and oxygen in the atmosphere, while allowing these gases to circulate in weather patterns that distribute energy and materials globally. Dr. James Walker's studies of planetary atmospheres show that losing just 10% of Earth's gravitational strength would allow atmospheric escape rates that would eliminate our atmosphere over geological timescales. The precise balance becomes apparent when you consider planetary formation itself. Gravity must be weak enough to allow gradual accretion of planetary building blocks over millions of years, without immediate collapse into stellar masses, yet strong enough to overcome gas pressure and electromagnetic forces to accumulate planetary mass objects from cosmic dust and debris. Dr. Alan Boss's computer simulations of planetary formation show that this process requires gravitational strength within narrow ranges compared to other fundamental forces. Earth's mass of 6 kilograms represents a gravitational accumulation perfectly suited for biological evolution. This mass creates surface gravity strong enough to retain atmospheric gases while allowing complex, multicellular organisms to develop structural systems capable of supporting their own weight. Dr. Robert Berner's studies of atmospheric evolution show that Earth's gravitational field has maintained atmospheric pressure and composition within ranges compatible with life for over 3 billion years. The relationship between gravity and biological scale becomes critical when examining how life can evolve from microscopic to macroscopic complexity. Single-celled organisms operate in environments where electromagnetic forces dominate and gravity is negligible. But multicellular life requires gravitational fields strong enough to provide consistent orientation cues while remaining weak enough to allow complex structural solutions to gravitational stress. Dr. J.B.S. Haldane's classic essay on being the right size demonstrated that biological scaling laws depend critically on the relative strength of gravitational and electromagnetic forces. Insects can support their body weight using thin, lightweight exoskeletons because their small size makes gravitational forces negligible compared to electromagnetic forces in their structural materials. Larger animals require increasingly sophisticated skeletal and muscular systems to overcome gravitational stress. The evolution of life from aquatic to terrestrial environments illustrates gravity's biological importance. In water, buoyancy largely cancels gravitational effects, allowing marine organisms to achieve large sizes without complex structural support systems. The transition to land required evolutionary innovations, internal skeletons, muscle systems, circulatory systems capable of pumping fluids against gravity, that demonstrate how biological complexity increases as organisms encounter stronger effective gravitational forces. Dr. Stephen Jay Gould's studies of evolutionary scaling show that maximum organism size on land is limited by gravitational stress on biological materials. The largest land animals approach the limits imposed by the strength of bone and muscle tissue under Earth's gravitational field. In environments with stronger gravity, large complex organisms would be impossible because biological materials couldn't support their own weight. Plant evolution provides another perspective on gravity's biological necessity. Plant growth depends on gravitropism, the ability to sense and respond to gravitational fields, for proper root and shoot orientation. Dr. John Kiss's research on plant gravity sensing reveals that plants have evolved sophisticated cellular mechanisms for detecting gravitational acceleration as small as 0.1% of Earth's surface gravity. This sensitivity allows plants to maintain proper orientation for photosynthesis and nutrient absorption. The absence of adequate gravitational cues creates significant problems for biological development, as demonstrated by experiments on organisms grown in microgravity conditions aboard the International Space Station. Dr. Annalisa Paul's studies of plant growth in space show that reduced gravitational fields disrupt normal development patterns, cellular organization, and physiological functions that depend on gravity-guided growth and fluid transport. Animal physiology also depends critically on gravitational effects for proper development and function. The human cardiovascular system evolved to pump blood against Earth's gravitational field, requiring heart muscle strength precisely calibrated to overcome gravitational resistance while maintaining circulation to the brain and extremities. Dr. Charles Science studies of astronaut physiology show that extended exposure to reduced gravity causes muscle atrophy, bone density loss, and cardiovascular deconditioning that can become life-threatening. The inner ear organs that provide balance and spatial orientation in vertebrates represent evolutionary solutions to living in gravitational fields. These otolith organs contain dense calcium carbonate crystals that move in response to gravitational acceleration, providing the nervous system with information about body orientation relative to local gravitational fields. Dr. Muriel Ross's research shows that these gravity-sensing organs are essential for normal motor control and spatial navigation in complex organisms. Gravity's weakness also enables the atmospheric and hydrological cycles that sustain life over geological timescales. Earth's atmosphere can maintain convection patterns that transport heat and moisture globally because gravitational forces are strong enough to prevent atmospheric escape, but weak enough to allow buoyancy-driven circulation. Dr. Carrie Emanuel's studies of atmospheric dynamics show that this balance depends on gravity being within narrow ranges compared to thermal energy scales in atmospheric gases. The geological processes that maintain planetary habitability also depend on gravity's precise weakness. Plate tectonics, the slow movement of Earth's surface that recycles carbon dioxide and maintains climate stability, requires gravitational forces strong enough to drive convection in the planet's mantle, while remaining weak enough to allow solid rock to flow slowly over geological timescales. Dr. Paul Silver's research on mantle dynamics shows that this geological activity requires gravitational and thermal energy scales to be precisely balanced. Ocean tides created by lunar and solar gravity demonstrate another aspect of gravity's biological importance. These tidal cycles have influenced biological evolution for billions of years, creating intertidal environments where early life may have made the transition from marine to terrestrial existence. Dr. Kurt Strobeck's studies of circadian rhythms show that many biological processes remain synchronized to tidal and lunar cycles, indicating that gravitational effects have shaped biological evolution at fundamental levels. The long-term stability of planetary orbits that maintain consistent solar energy input over billion-year timescales depends on gravitational interactions between planets, remaining stable despite chaotic perturbations from other celestial bodies. Dr. Jacques Lasker's calculations of solar system dynamics show that Earth's orbital stability over geological time depends on gravitational forces being precisely balanced to maintain near circular orbits despite gravitational perturbations from other planets. Recent discoveries of exoplanets and other stellar systems reveal that most planetary configurations are far less stable than our solar system, with planets in highly elliptical orbits, massive planets migrating close to their stars, and gravitational interactions that would make long-term biological evolution impossible. Dr. Alan Boss' surveys of exoplanetary systems suggest that gravitational configurations suitable for billion-year biological evolution may be relatively rare in the cosmos. Understanding gravity's role as life's foundation reveals that biological complexity requires an incredibly precise balance between gravitational effects and other physical processes. Life needs gravity to be weak enough not to disrupt chemistry and strong enough to create stable planetary environments. This balance must be maintained across scales from molecular chemistry to planetary physics, suggesting that the observed strength of gravity relative to other forces might be precisely fine-tuned to allow biological evolution. The implications extend beyond Earth to questions about life throughout the cosmos. If gravity's strength is indeed fine-tuned for biological complexity, then life might be possible only in universes where fundamental force ratios fall within narrow ranges. This fine-tuning might explain why consciousness exists to observe the cosmos. We find ourselves in a universe where gravity has exactly the strength necessary to make observers possible. Life's foundation in gravity's weakness reveals that biological evolution is not separate from cosmic evolution, but intimately connected to the fundamental structure of physical law. The emergence of consciousness depends on the same gravitational fine-tuning that creates stars, planets, and cosmic structure, suggesting that mind and cosmos are linked through the precise weakness that makes complexity possible at every scale from atoms to galaxies. Chapter 8. Future Implications. Gravity's mysterious weakness holds profound implications for the future of physics, technology, and humanity's understanding of reality itself. As we develop increasingly sophisticated theories about extra dimensions, quantum gravity, and unified field theories, the puzzle of gravity's feebleness continues to drive revolutionary discoveries that could transform our comprehension of space, time, and the fundamental structure of existence. Understanding these future implications reveals why solving gravity's weakness mystery might be the key to unlocking reality's deepest secrets. The search for quantum gravity represents one of the most important frontiers in theoretical physics, driven partly by the need to understand why gravity is so incredibly weak at quantum scales. Dr. Carlo Rovelli's loop quantum gravity theory proposes that space and time themselves are quantized, composed of discrete units rather than smooth continua. In this framework, gravity's weakness emerges because smooth spacetime geometry only appears when enormous numbers of quantum geometric units combine together, similar to how smooth water emerges from countless discrete molecules. String theory approaches the quantum gravity problem by proposing that all fundamental particles are actually vibrating loops in higher dimensional space. Dr. Michael Green and colleagues have shown that gravity's weakness in string theory results from gravitons, hypothetical particles that carry gravitational force, being able to propagate through all spatial dimensions while other force carriers remain confined to lower dimensional subspaces. This dimensional explanation might eventually lead to testable predictions about extra dimensions and gravity modification. The technological implications of understanding gravity's weakness could be revolutionary. If gravity can indeed be modified or enhanced by accessing extra dimensions or quantum effects, future technologies might achieve gravitational control for propulsion, manufacturing, and energy generation. Dr. Robert Forward's theoretical studies of gravity modification suggest that controlled gravitational fields could enable spacecraft propulsion without reaction mass, manufacturing processes that operate in controlled gravity environments, and energy generation through gravitational field manipulation. But current physics suggests that gravity modification faces fundamental obstacles related to energy requirements and quantum limitations. Dr. Matt Visser's calculations show that creating artificial gravitational fields strong enough for technological applications would require energy concentrations approaching those found in black holes or neutron stars. The weakness of gravity that makes it negligible at small scales also makes it incredibly difficult to manipulate artificially. Recent experimental tests of general relativity are pushing toward the regimes where gravity's weakness might reveal new physics. Dr. Rainer Weiss, Nobel Prize winner for LIGO's development, predicts that next-generation gravitational wave detectors will be sensitive enough to observe quantum effects in gravitational fields, potentially revealing whether gravity truly becomes strong at quantum scales or remains mysteriously weak even in the quantum realm. These observations could provide the first direct evidence for quantum gravity theories and illuminate why gravity behaves so differently from other fundamental forces. The cosmic implications of gravity's weakness extend to the ultimate fate of the universe itself. Current observations suggest that dark energy, a mysterious form of energy that affects cosmic expansion gravitationally, will continue accelerating the expansion of space forever. Dr. Lawrence Krauss's calculations show that this acceleration will eventually carry all other galaxies beyond our observable horizon, leaving our local group isolated in an apparently empty universe. If gravity's weakness prevents the development of technologies capable of intergalactic travel, as discussed in previous chapters, then the accelerating expansion driven by dark energy represents a cosmic isolation that no intelligence can overcome. Future civilizations will inherit increasingly empty universes where evidence of cosmic evolution and the existence of other galaxies gradually disappears beyond observable limits. But understanding gravity's weakness might also reveal unexpected possibilities for cosmic connection. If gravity operates through extra dimensions, advanced civilizations might eventually develop technologies that access these dimensions for communication or travel. Dr. Lisa Randall's work on warped extra dimensions suggests that signals or even matter might propagate through higher dimensional space at speeds faster than light in our three-dimensional space, potentially enabling forms of cosmic communication that circumvent relativistic limitations. The unification of gravity with other fundamental forces remains one of physics' greatest challenges, largely because of gravity's extreme weakness compared to electromagnetic, weak nuclear, and strong nuclear forces. Grand unified theories attempt to show that all forces become comparable in strength at extremely high energies. But gravity remains mysteriously weak even at the highest conceivable energy scales. Dr. Steven Weinberg's work on effective field theories suggests that gravity's weakness might be a low-energy manifestation of more fundamental physics operating at energy scales far beyond current experimental reach. At the Planck energy scale, approximately 1019 GeV, quantum effects and gravitational effects should become comparable, potentially revealing why gravity appears so weak at lower energies. String theory predicts that gravity and other forces might unify only in higher dimensional spaces with 10 or 11 total dimensions. Dr. Edward Witten's Infori framework suggests that our three-dimensional space might be a small part of a vast 11-dimensional structure where all forces are unified. Understanding this unification might require developing technologies capable of accessing or manipulating extra-dimensional space. The anthropic implications of gravity's weakness continue to generate philosophical debates about cosmic fine-tuning and the possibility of multiple universes. Dr. Martin Rees's studies of cosmic fine-tuning show that gravity's strength relative to other forces must fall within narrow ranges to allow stars, planets, and life to exist. This fine-tuning might indicate that we live in one of many possible universes with different force ratios. Observing these particular values because they're necessary for observers to exist. Alternative theories propose that gravity's weakness might be dynamical rather than fundamental, changing over cosmic time or varying across different regions of space. Dr. John Maguio's varying fundamental constants theories suggest that force strengths might have been different in the early universe, potentially solving cosmological problems while explaining current observations through cosmic evolution of physical laws themselves. Recent advances in quantum information theory suggest that gravity's weakness might be related to the holographic principle and the fundamental relationship between space and information. Dr. Juan Maldacena's SADS-CFT correspondence shows that gravitational theories can be exactly equivalent to non-gravitational theories operating on lower dimensional boundaries, suggesting that gravity might not be fundamental, but rather an emergent property of information processing. If gravity is indeed emergent from information, then understanding its weakness requires developing theories about how information creates the appearance of space, time, and gravitational force. Dr. Mark van Romstunk's work on quantum entanglement and spacetime suggests that gravitational effects might arise from quantum entanglement networks, potentially explaining why gravity appears weak. It might be constructed from numerous weak quantum correlations rather than being a fundamental force. The technological applications of emergent gravity theories could be transformative. If spacetime emerges from information processing, then manipulating information might allow direct control over gravitational effects. Quantum computers might eventually become capable of simulating or even creating gravitational fields by manipulating the information processing that gives rise to spacetime geometry. Dr. John Preskill's research on quantum computation and gravity suggests that advanced quantum computers might be able to test theories about emergent spacetime by simulating the information processing that creates gravitational effects. These simulations could reveal whether gravity's weakness results from information theoretic principles rather than fundamental force hierarchies. The search for dark matter and dark energy, which interact gravitationally but remain mysterious to all other forces, might also illuminate gravity's weakness. If gravity is the only force that couples to hidden sectors of reality comprising 95% of the universe, understanding this coupling might reveal why gravity appears weak in our observable sector while potentially being strong in hidden cosmic components. Future dark matter detection experiments and dark energy observations might reveal whether gravity behaves differently when interacting with dark components compared to ordinary matter and energy. Dr. Sean Carroll's theories about dark energy suggest that understanding cosmic acceleration might require new insights about gravity as fundamental nature and its relationship to the vacuum structure of spacetime. The implications extend beyond physics to questions about consciousness and the relationship between mind and physical reality. If gravity's weakness is precisely tuned to allow complex information processing in biological systems, then understanding this tuning might reveal deep connections between physical law and the emergence of consciousness throughout the cosmos. Future implications of solving gravity's weakness mystery might include discovering that consciousness itself plays a role in determining the strength of fundamental forces, or that the precise weakness observed results from anthropic selection effects in a vast multiverse where consciousness can only emerge in universes with exactly these force ratios. Understanding gravity's weakness represents a frontier where physics, cosmology, information theory, and philosophy converge toward potentially revolutionary insights about the nature of reality itself. The future discoveries emerging from this research might transform not just our understanding of forces and particles, but our comprehension of space, time, consciousness, and humanity's place in the cosmic order.